State and prove the Sturm's fundamental comparison theorem. Now statement: let phi of 1x be the solution of the differential equation do dx of px into dy upon dx plus q1xy equals to 0, and phi to be the solution of the differential equation d over dx px into dy upon dx plus qx q2xy equals to 0. Equation 2: on the interval a is less than equal to of x is less than equal to of b, let p have a px have a continuous derivative. These are equation 1 and 2, and is such that p of x is greater than 0, and let q1x and q2x be the continuous and are such that q2x is greater than q1x. Then if x1 and x2 are the two consecutive zeros of phi 1 on closed interval AB, and phi 2 must have at least one zero at a same point on the open interval x1 is less than x is less than x2. Now proof: let us assume that phi 2 does not have a 0 on the open interval x1 is less than x is less than x2. Then without any loss of generality, we have assumed that phi 1x is greater than 0 and phi 2x is greater than 0 as x1 is less than x is less than x2. Since phi 1x is a solution of equation 1 and phi 2 is a solution of equation 2, therefore we have d over dx of px phi 1 dash x plus q1x phi 1x equals to 0. Equation 3, and d over dx of px phi 2 dash x plus q2x phi 2x equals to 0. Equation 4, multiplying 3 by phi 2x and 4 by phi 1x, we get phi 2x d over dx of px phi 1 dash x plus q1x phi 1x phi 2x equals to 0. Equation 5, and phi 1x d over dx of px phi 2 dash x plus q2x phi 1x and phi 2x equals to 0. Equation 6, subtracting 5 and 6, we get phi 2x d over dx of px in phi 1 dash x minus phi 1x d over dx px phi 2 dash x equals to q2x minus q1x into phi 1x into phi 2x, or d over dx of px phi 2x phi 1 dash x minus phi 1x into phi 2 dash x equals to q2x minus q1x into phi 1x into phi 2x. Integrating both sides between the limits of x1 and x2, we get integral x1 to x2 d over dx of px into phi 2x of phi 1 dash x minus phi 1x into phi 2 dash x dx equals to integral j x1 to x2 q2x minus q1x into phi 1 and into phi 2x dx, or p of x into phi 2x phi 1 dash x minus phi 1x phi 2 dash x limit x1 to x2 equals to integral x1 to x2 q2 minus q1x into phi 1 phi 2 x dx, or px2 into phi 2 x2 phi 1 dash x2 minus phi 1 x2 phi 2 dash x2 minus p x1 into phi 1 dash x1 phi 2 x1 minus phi 1 x1 into phi 2 dash x1 equals to integral x1 to x2 q2 minus q1 into phi 1x into phi 2x dx. Since x1 and x2 are the zeros of phi 1, and therefore phi 1x1 equals to 0 and phi 1x2 equals to 0, hence p of x2 into phi 1x2 and phi 2x minus p of x1 into phi 1 dash x1 and phi 2 x2 equals to integral x1 to x2 q2 minus q1 into phi 1x into phi 2x dx. Equation 7. Now by the hypothesis p of x2 is greater than 0, since phi of x2 is equals to 0 and phi of x1 is greater than 0 for all values of x1 and x2. Therefore we have phi 1 dash x2 is less than 0, since phi 2x is greater than 0 on x1 is less than x2. Therefore phi 2x2 is greater than equal to of 0. Thus p of x2 phi 1 dash x2 into phi 2x2 is less than 0. Similarly, we can show that p of x1 into phi 1 dash x2 into phi 2 x1 is greater than 0. This gives that the left hand side of the member of the 7 is not positive, but the hypothesis of q2x minus q1x is greater than 0 on x1 is less than equal to of x is less than equal to of x2, and so the right hand side of the member of the 7 is a positive. Thus the assumptions that phi 2x does not have a 0 on the open interval x1 is less than x is less than x2 leads to a contradiction, and so the phi 2x has a 0 at same point of this open interval. Hence the phi 2x must have a 0 between the two consecutive zeros of phi 1x.